In these next segments, we're going to take a look at sampling distributions. Specifically, we're going to talk about the sampling distribution, the sample mean, and the central limit theorem in this particular video. The learning objectives. What do we want to come out of this series with? We want to be able to understand the similarities and differences between a population distribution and a sampling distribution. We want to use the central limit theorem to describe a sampling distribution. We need to be able to compute the probabilities associated with a sampling distribution and understand the relationship between sample size and the standard deviation of the sampling distribution. First of all, when we talk about a sampling distribution, we're talking about the sampling distribution or the distribution of a sample statistic. And here's the concept. The basic idea is, suppose you had a population of size cap n. Remember, we use a capital letter N to represent the population size. Now, if you go to that population, you take all possible samples of size little n. As you recall, we use little n, lowercase n, to represent the sample size. And then from each of those samples, we calculate the sample mean. So when we're done, what we're going to end up with is a bunch of sample means. Now, each sample mean is nothing but a number. So if I take a look at the distribution of all those numbers, all those sample means, that is, so we just basically established the sampling distribution of the sample mean. Now, let's do that again, only think of it this way. If I walk up to you, you're sitting at your desk, you get your calculator out, and I take a bucket, I dump a bunch of numbers on your desk. And I say, okay, first of all, I'm going to tell you about these numbers is that the measurement scale is at least interval. That means, obviously, it's going to be interval or ratio, which means you can calculate means, and distances make sense. You can do the typical arithmetic. So, if I say, hey, take a look at those numbers, and I'll be back in a few minutes, tell me what you can about the distribution of those numbers. What would you do? Well, you calculate probably the mean, the standard deviation that tells me how the data is spread out. You may do like a histogram or box plot, look at the shape, report possibly the median. You can describe what the distribution looks like. You can give me estimates for the parameters by using the statistics. Now, after you do that, I say, oh, by the way, I forgot to tell you, each of those numbers is actually a sample average. So that number, you pick any number out of that data set, and that number is actually the average of a bunch of other numbers. Well, now that distribution describes the distribution of those means, because each number is a mean. The concept is the same. If we know the parameters that specify this distribution, then we can calculate probabilities based on the distribution. Let's go back and talk about the binomial for a second. You were able to calculate probabilities from the binomial distribution because you knew the parameters. If you know n, the sample size, and you know pi, the true probability or the theoretical probability, and you know the scenario you're working on fits the assumptions for a binomial, then you can calculate any probability you want about that binomial because you have the parameters. The only parameters you need for a binomial is n and pi. Well, in the previous sections, we talked about the normal distribution, and we said all you needed to calculate a probability based on a normal distribution was mu, the true mean, the population mean, and sigma. So the population standard deviation. So if we know the parameters that specify the sampling distribution, then we can calculate probabilities about sample averages. Now, three very interesting things occur when we do this for a sample mean. Do this meaning we go out and take all possible samples of size little n and calculate all the averages and then look at the distribution. The first thing is regardless of the parent distribution is a population. Regardless of what that looks like, I don't care if it's normal, if it's bimodal, if it's skewed right, skewed left, if it's just a disaster, it's all over the place, it doesn't matter. Regardless of what the distribution looks like for the population, the averages, the distribution of the averages will have a mean that's equal to mu, the true population mean. It doesn't matter what the distribution look like. If you take all possible samples of the same size, the average of the averages will be mu, the population mean. The variance for the sample means will be sigma squared, which is the population variance, divided by n, the sample size. Now, if we add to that, if we know that the parent distribution, if we know the population actually happens to be normal, okay, if the parent distribution happens to be normal, then we can say, gosh, the average is x bar. The distribution of x bars will also be normal, And the parameters will be, yeah, you guessed it, mu and sigma squared over n. So now, with this, we could actually start calculating probabilities regarding sample averages. Now, if you think about this, this is really the exact same thing we just did in the previous chapter. In the previous chapter, we said x is distributed normal with a mean of mu and a variance of sigma squared. Well, all the questions we asked were like, what's the probability of reaching into or selecting somebody at random from this population and that individual's IQ score is at least 120? The individual, n was 1. Well, if we divide this by n, it's always going to be divided by 1. So why even bother? In reality, all we're doing now is we're saying we have more than 1. We have not an individual, but we have averages. So if I have averages, I need to account for the fact that this observation is no longer one observation. It's based on n observations. So n has always been there. It's right there. Just because it's been a 1, we never bothered with it. Okay, that's, see, 1, 2 things are cool. And the third thing that's cool is if the sample size is large enough, then the CLT will apply. And we can reasonably assume that x bar will be distributed normal with a mean of mu and a variance of sigma squared over n. Now, you're asking, what the heck is the CLT? The CLT stands for the central limit theorem. Now, notice in this third thing that happens is we're saying if the sample size is large enough, then the CLT will apply, and we can claim that this is reasonable. There's nothing here about what the parent population was. It doesn't matter if the population is heavily skewed, if it's bimodal, if it has to be uniform or normal. It doesn't make a difference. Simply, if the sample size is large enough, regardless of what the parent distribution looks like, we can make this claim. Previously, we just got done saying we can make this claim if the population was normal. So if we know the population is normal, this is reasonable. If we don't have any information about the population, but the sample size is large enough, and of course you're thinking, what is large enough? And we'll talk about that in a second. But if the sample size is large enough, then the central limit theorem will apply, and we can still have these parameters that we need to calculate probabilities regarding averages. Okay, the central limit theorem says that as the sample size increases, the sampling distribution, the sample means becomes normal. So as n gets larger, little n gets larger, it becomes normal, it being the distribution of the sample means. Now, what does it mean to be big enough? Well, typically this is considered to be at least 30. So if we have a sample size of at least 30, then the sample means, well, we feel pretty confident in saying that the sampling distribution of the sample means is approximately normal. Now, this is really just a rule of thumb. It's not carved in stone in any place. It's really more of a guideline. And the actual sample size that's required will depend a great deal on the shape of the parent distribution, just what the population looks like. If the population is normal to begin with, forget it. It doesn't matter what your sample size is. The means are going to be normal. It doesn't really matter. If you have something that's really heavily skewed, then you could need that more than 30. But we see empirically means something we actually observe when messing around with different distributions, that around 30 seems to be the magic number that it starts to converge and it looks pretty good. It's pretty reasonable at 30. Let's suppose that our distribution was uniform. Well, uniform symmetric. Any symmetric distribution will become normal very, very quickly. Well, when I say it will become normal, I'm really saying that the means, the sample means that came from a bunch of samples from that distribution, the sample means will become normal. The distribution is what it is. The parent distribution is what it is. It doesn't change. Okay, the central limit theorem may be one of the most important theorems in basic statistical analysis. The reason is, the big reason is that it provides us with a distribution so we can calculate probabilities regarding the sample means, regardless of the population. Regardless of the population simply means it doesn't really matter what the population looks like, as long as the random variable is at least interval scale. We wouldn't do this with something that's nominal or ordinal. That wouldn't make any sense. Okay, let's calculate some probabilities here real quick. Here's a scenario. Recent scores of 12th grade students on the National Assessment of Educational Progress has a distribution that is reasonably normal. That's kind of important. I'm going to underline that guy. It's reasonably normal with a mean of 300 and a standard deviation of 35. So I'm going to write that down someplace too. It says the mean, mu, is 300, and the standard deviation, that's got to be sigma, is 35. Find the probability that a single randomly chosen student has a score of at least A, 300, and B, 350. Well, what's the assumptions? The assumption here is that the distribution is normal. Now, you notice this is a single student, a single randomly chosen student. So I'm talking about X, not X bar. This is reasonable because we're told. Right here, we're told that the distribution is normal. So no big deal. Now, to calculate probability, I'm going to do like we did previously. For the first one, I'm going to start with a probability statement. I want to know the probability that X is at least 300. If I draw a picture, well, the mean on this distribution is 300. I want the right tail. So I'm done. This equals 0.5. Remember, it's symmetric, so you have half above the mean, half below. So I don't even need to go to a calculator. But if I did go to a calculator, I'd use normal CDF. Lower bound is 300. Upper bound is infinity, which we use E99. The mean is 300. And the standard deviation was 35. If you do that, it's going to come up and tell you it's 0.5. You can go ahead and verify it if you like. Okay, this second one here. This next one says, what's the probability that a random student is at least 350? Well, again, I'm going to draw a picture. 300 is the mean. 350 is up here someplace. Doesn't matter where. I'm just using this for illustration to make sure I do the right thing. I want greater than 350, so I'm shading in the area I want. So this I would use normal CDF. 350 E99. The mean's 300, standard deviation is 35. And when I do that, I get, gosh, I don't know. Let's go to the calculator real quick. Actually do it. So if I go second distribution, I want normal CDF. See, I need 350 to infinity, E99. The mean's 300, standard deviation is 35. Hit enter, and I get 0.0765, yada, yada, yada. Now, I'm glad this happened because quite often I get questions as why is it that I have so many numbers and sometimes I only have 4. As a standard, as convention in my courses, I always have students go out 4 places. So I want to do this again, but I want to fix my calculator so it only goes out 4 places. If I hit the mode button, you see it toward the top, then go down to float and over to 4. This is telling it to round off at that 4th place. So I'll do second quit, get out of there. If I do second enter, it brings up my last command. Just hit enter again to execute it, and there it is, rounded off. So the answer was 0.0766. So based on this information, the probability that a randomly chosen student would have a score of at least 350 is a little over 7%. 0.07. Another interpretation is roughly 7.6% of all the students had scores greater than 350. Now, what did that have to do with the central limit theorem? Nothing. Absolutely nothing at all. However, I want to ask that same question, only this time it's going to be based on the group of 26 students, because in reality, that's what we're interested in. Very seldom are we interested in what happens with one individual or one object. We're really looking at what typically happens to a group. And typically is another way of saying the mean or the median. So, we have the same scenario, the exact same scenario, and this time we have a group of 26 students. Now, the assumption here is going to be that x bar is distributed normal, specifically with a mean of 300 and a variance of 35 squared over 26. You know, I need to redo that. I'm sorry, I just kind of crammed that in there. Let's try that again. X bar distributed normal with a mean of 300. And this, remember, the standard deviation was 35, so the variance is 35 squared divided by n, which is 26. So the square root of all of this will be my new standard deviation. Okay, find the probability that a randomly chosen a group of 26 students had an average score of at least 300. Well, I'm going to use this area to draw my picture. This is saying, look for the probability that x bar is at least 300. Well, if I draw that picture, the mean is 300. I'm looking for this. Oh, it's 0.5. Well, that didn't change. Look at the previous one. The mean's still 300. Probability of being above the mean, because it's a normal distribution, is still going to be a half. When we change the standard deviation, all we're doing is we're making the curve tighter. It's not spread out as much. But the mean is still down the middle. So probability being greater than the mean is always going to be a half. Okay, now find the probability that a randomly chosen group of 26 students had an average score of at least 350. Well, the assumptions are the same, so I don't need to address that again. And oh, you know what? I wrote the assumptions down here, but I didn't say why they're reasonable. Why is this reasonable? Well, it's reasonable for the same reason it was when we did this one. We were told that the distribution is reasonably normal. This is reasonable because we were told so. Okay, back to this. I want to know the probability of an average score being at least 350. So our probability statement is going to look like the probability x bar, I'm talking about the averages now, is at least 350. Well, if I draw my picture, the picture is going to look exactly like I did a moment ago when I was only talking about one student. It's the same thing. 300, 350. I'm looking for this area. Remember, x bar is distributed normal with a mean of 300 and a variance of 35 squared over 26. So now I would go to normal CDF. The lower bound is, oops, I'm sorry. This is supposed to be 350. Glad I saw that. The lower bound is 350. The upper bound is infinity, E99. The mean is 300. Wait, that was right to begin with. Oh, I'm having a rough day. The mean is 300. The probability statement is greater than 350. Okay. I'm back with it. This is exactly what we did earlier, but what's about to change is the standard deviation. The standard deviation, sigma, is going to equal the square root of 35 squared over 26, which equals 35 divided by root 26. So this is 35 divided by root 26. That is what changed. So now let's go to our calculator and take a look. I'm going to clear this other stuff off and go back to second distribution, normal CDF. I want 350 to infinity. The mean is 300. The standard deviation is now 35 divided by square root of 26. That is 1.6287 e negative 13. All right, let's take a look at what that means. And actually, we've had probabilities like that before. This is 1.6287 e negative 13. This is scientific notation. It's telling you to take the decimal, move it to the left 13 places. This is 0 point, wow, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros and a 1, 6, 2, 8, 7. No, we don't carry that far out. We're basically only going 4 places. So we would say that this is about, or approximately, 0.0000. Now, we've already had this discussion, but just as a reminder, when I say the probability is 0.0000, I'm not saying it's 0. That's saying it's 0 out 4 places. Out there somewhere else that there's more. But it's so small, who really cares? Now, think about this for a second. Why on earth did this change so much? This probability, I'll go back a little bit more. This probability is a little over 7%. Same picture. This probability is, for all practical reasons or purposes, almost 0. What's the difference? Well, the difference is, if this is my distribution, here's 300, here's 350. To get a single value above 350 is no big deal. But to get an average above 350, that means that if I did a sample of 26 people, I'd have to have a score here, 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 here. If there's somebody down here, I need somebody, a couple up here to offset it. Because remember, the average is a balancing point. So I need data that has a balancing point, an average at 350. That means all 26, or the vast majority of them, need to be very, very, very high. How likely is this to happen by random chance? If you take a random sample from a distribution that looks like this, wouldn't you expect at least to get somebody down here? But, I mean, it could, but if you did, you'd have to have, like I said, somebody way up here to balance it out. And that's just all that likely to happen. So that's why this probability is extremely small. The other thing is the standard deviation was 35 for the original distribution, right? Well, between 350 with a standard deviation of 35, that's less than 2 standard deviations away. But 35 divided by square root of 26, this is talking general terms. Square root of 26 is almost the square root of 25, which is 5. So the standard deviation is just a little bit bigger than 5. So it went from 35 down to about, 35 divided by 5, which is 7. So it went to roughly 35 all the way down to approximately 7. Well, between 300 and 350, how many times does 7 go in there? About 7 times. So this is actually about 7 standard deviations away when we're talking about the sample averages with a distribution that has a standard deviation of 35 over square root of 26, where with the original distribution, it simply had a standard deviation of 35. This is less than 2 standard deviations away. So 350 is really, for the distribution that looks like this, normal with a mean of with a mean of 300, and a variance of 35 squared over 26. That means the standard deviation is 35 over the square root of 26. This is a long way away from the mean. If we're going to try to draw this a little bit more accurately, now that we know how many standard deviations this guy is, and you can convert this to a z-score and see how far it really is, this 350 is going to be like up here someplace. Way, way up here. Okay, that'll wrap it up for the idea of the central limit theorem as it applies to these sample averages and calculating probabilities based on the central limit theorem for the sample averages.